Hi guys, welcome to Learn Electronics Repair. So today we're going to talk about the TL431. In fact, this is all you need to know about TL431 to fix stuff. So what is a TL431? Well, there's one there. It looks like a transistor. It looks just like a transistor. T092 package. But it's not, and you can probably see here the pins are not marked emitter, base collector or EBC in whatever order they are: K, A and R. That's cathode, anode and reference. And the TL431 basically is a Zener diode, but it's a programmable one. So a Zener diode, which we'll just talk about briefly in case you're not so familiar with them, is a type of diode that is used as a voltage reference that will have a certain voltage across it which is stable whenever the supply voltage is higher than the Zener voltage. Okay, so if you have a Zener diode, 12 volt Zener, and you put more than 12 volts across it, the Zener diode will maintain the 12 volts. This does exactly the same thing. It's just programmable. By putting the voltage on the reference pin, you can change the Zener voltage. And why is this important? Well, these components are everywhere. But one particular usage of them is in this sort of circuit. This is a small switch mode power supply, and on switch mode power supplies of all sizes, you will almost always see an opto isolator, and nearby it will be this thing, TL431. Sometimes, like this one, they are marked with a different prefix. This is KIA431. You'll find other ones, LM431, TL431 and so on. Just different manufacturers, but they're all the same thing. So let's have a look first on paper what this thing does. Then let's play around with some of these. Let's learn how to test these out of circuit, and then let's look at how this works with the opto isolator to regulate the output voltage of a power supply. And finally, let's have a look to see how we can test this whole setup in circuit. Okay, the TL431 and the opto isolator and all the associated components. Okay, so first thing first then, let's get the paper out. To understand the TL431, first thing we need to do is understand what a Zener diode is. So a Zener diode, as I mentioned, is effectively a voltage reference. If you take a supply voltage, which is now on the paper, we take a supply voltage, we connect a resistor, and we connect our Zener diode like so. This is ground, 0 volts, and this is, we'll put plus VCC, supply voltage, okay? If we connect from ground to here, across the Zener diode, this is the anode, this is the cathode, C or K, whichever you prefer. Once the supply voltage goes above the Zener voltage, which is the rating of this diode, the voltage here will become stable. So if, for example, this was a 12 volt Zener and we increase the voltage on here, while the voltage here is below 12 volts, the voltage here will increase at the same time as that voltage. I'll show you this, we'll do it in practice. We have a resistor to limit the current flowing through the diode. The value is not critical in most cases. I'm going to use a 1K resistor. And you'll see that once the voltage at this end of the Zener reaches 12 volts or very close to that, I can continue to increase the voltage here, but that will stay the same. So let's do this now with a Zener diode so that we're certain how this works, and then we can see how we can replace this with the TL431 and what the advantages of doing so are. To test this, I've made a very simple circuit on this piece of breadboard. So I have a 1K resistor connected to the positive of my power supply, a variable one. At the moment it's set basically to 0 volts. this meter is monitoring the input voltage. The resistor then connects to a Zener diode to the cathode, and this end connects to ground. So a Zener diode actually connects in the reverse direction to a normal diode. It's the reverse breakdown voltage that sets the Zener voltage. So from the junction of the resistor and the diode, I have a wire going here to this multimeter. So this multimeter is measuring the voltage across the Zener, and this is measuring the input voltage. Now let's see what happens. So I'll turn the supply voltage up, about 2 volts now, and you'll see that the voltage across the Zener and the voltage across the resistor are basically the same. And we can continue to increase the voltage. This is a 12 volt Zener. You can see 8.8 volts on both now, basically the same voltage on both sides. And we continue to go up, 11. Now I'm getting near to the rated voltage of this Zener. So let's see what happens when we get to 12. We're at 12 now. I'll continue to increase the supply voltage. Now look what's happening. The Zener voltage is 12, and although I increase the supply voltage up to about 20 volts now, it's still 12. Okay. So the Zener gives us a stable voltage regardless of the supply voltage. The resistor is here to limit the current flowing through the Zener. If the current becomes too much through the Zener, then it will burn out. Now there's something that should be extremely obvious from what I've just done, but I'm going to make it even more obvious by showing you. I've modified the circuit a little bit, guys, you can see it there. So what I've actually done is added an LED in series with the resistor and the Zener. So we still have the resistor from the supply voltage coming in, which is variable, which now goes to our LED, and then the LED connects to the Zener cathode, and this is connecting to ground. You'll clearly see now that a Zener diode works in the reverse polarity, if you like, the reverse direction to a normal diode. In fact, if you connect a Zener diode the other way around, it is just a diode, okay? An LED is also just a diode. It just happens to light up and have a higher voltage drop, but basically it is a diode, okay? So let's see what happens now. We're going to measure the voltage again across the Zener. Well, we don't have much at the moment. And see what's happening now. The voltage on the input is increasing, but the voltage on the Zener is not. And it won't until I reach the point where the diode junction in the LED is overcome. So at about 1.7 volts, 1.8 volts there, 1.9 volts, that LED is now conducting in the forwards direction. And the voltage we see between the 2 meters, 0.6 on the left hand side, 2.5 on the right hand side, is a voltage drop across the LED. Why isn't the LED lit up? Why isn't it lit up? Well, the reason it's not lit up is because until the Zener diode starts to conduct, i.e. it has 12 volts across it, the LED can't light up because it can't pass any current. Okay? When I say can't pass any current, you're saying why is there a reading on here? The LED is passing a very small current, but only the current this meter requires to make a reading. This meter has about 10 mega ohm input impedance, so it's like putting a 10 meg resistor in series with your LED. Yes, that will pass current, but it won't light up. Okay, let's go more. We're getting nearer to the Zener voltage now. We still have 6 volts across the Zener. We need to go higher. 8 volts, 10 volts. Remember, this is a 12 volt Zener, so at some point now the Zener will start to conduct. And the LED came on. See that? There. Suddenly. Not just like from dim to on, it basically came on. Yeah, with a very small adjustment. So input voltage at 14, it's not lit. And at 14.3, it is lit. Okay. I'll just get a little bit closer for you so you can see it. There. So there's a very precise point at which the LED lights. The same resistor that is limiting the current through the Zener is now limiting the current through the LED, and I can continue to increase the supply voltage. The LED is now on full brightness, it won't go any much brighter than that. And you can see we have 12 volts across our Zener, 18 volt supply. But the main point of this is that the LED lighting is at a very precise voltage point. And this is exactly what we need to make power supplies regulate at a certain voltage. Okay? So that is a Zener diode. Now let's have a look to see what the difference is between this and a TL431. Well, the main difference is that a Zener diode is a fixed voltage. So you buy a Zener, a 9 volt Zener, a 12 volt, a 5 volt, whatever you buy, that's what it is. So if I want to change the voltage at which this is triggering the LED, I need to change the Zener. And we can do the same experiment. So we can increase the supply voltage. The LED is not lit. Okay. You can see the difference between the two as the voltage drop across the LED. This, of course, the multimeter went to sleep. Let's keep going. And somewhere near here, this is a 9 volt. Well, there's 9 volt supply, but there's only 6.2 across the Zener because of the voltage drop of the LED, which I keep mentioning, but at least it makes the point obvious by now. Somewhere here, the Zener will trigger there. Okay, so we can see now with about 10 volt supply, 11 volt supply, somewhere in that region, it triggers. 11.2. At 10.8 it's off, 11.2 the LED is on. Okay, this is the symbol for TL431. There are a few variations on this symbol. I'll just draw this one. This is the one from Texas Instruments datasheet. This is the anode. This is the cathode. And this is the reference pin. R or ref. Okay. To use this, we have a resistor going to VCC, the supply voltage. This end connects to ground. And if we connect the reference directly to the cathode, like so, this gives us a 2.5 volt Zener. Okay. That is the same as a 2.5 volt Zener diode. If we want any other voltage Zener, it's quite simple. We use 2 resistors. So when we say this is a programmable Zener, that doesn't mean you need a TL431 programmer to program it. It basically means that the Zener voltage is set by the value of 2 resistors connected to ref. I'll draw it this side this time. It can be drawn either side. I've just a bit more space here. So to program our Zener, we use 2 resistors, one connecting to ground and one connecting to VCC. And the ratio of these 2 resistors, R1 and R2, will set the Zener voltage of this. This is literally the current limiter. This is what my 1K resistor was doing in the circuit I demonstrated. So that's the basic use of a TL431. So let's try this in our circuit we've just made. Let's put the TL431 in, connected like that, and we'll also try it with some resistors, and we'll see that we can vary the Zener voltage. To do that, I'll do the same thing, which is to put an LED in series here. So our LED is going to go in series here. And we will see that it lights up when we reach the Zener voltage on the TL431. Okay, I've connected up my power supply again, set the output to 0. We now have the little circuit that we see here. So this is basically the same thing. I've just substituted the Zener diode with the TL431 and I've connected the reference to the cathode. So this is now a 2.5 volt Zener, which means that when the voltage on the power input goes above 2.5 plus the forward voltage drop of that, which is about another 1.5, 1.8, it will light up. If we increase the supply voltage then, as we did before, you'll see that the LED starts to come on at a little bit of a lower voltage, so the TL431 does start to conduct. And then at 2.499, you can see there, the TL431 is now holding a stable voltage. In fact, it's 2.5 exactly. And I can increase or decrease the supply voltage. Okay. So we have a slightly different but very similar behavior. Okay, you can see it there. To work out the values of the resistors is very easy because you just go to a calculator. I'll link this one, circuiteasy.com. There are others, and you can just put in the values you want. So, for example, I can tell it I want to put a 1000 ohm resistor in here. I want to know what value R2 is going to be, so I'll just leave that blank. I want 5 volts to be the voltage. And hit calculate R2, and you see it's 1000. If I wanted 6 volts, we just change that, calculate 714 ohms, very accurate, okay? So we'll just set it to 5 volts, calculate, and we use two 1K resistors, which is very handy because that's just what I have in my hand. I've now connected this little circuit. It's just by chance these are 1K resistors. Normally you would actually use higher value resistors there because you don't want much current flowing down this way. I just have to have some. I could just put two 10Ks there if I liked. It'll work just the same. But if I now increase the supply voltage, you'll see this is the VCC, so this is the power rail if you like. When I get to that point there, so it's suddenly on, yeah, much brighter. So as the supply voltage went above 5 volts, it lit up. Okay. Now, in the most common usage for these, or at least the usage we're looking at today, which is in power supplies, this LED is actually part of the opto-isolator. And that's what signals to the pulse width modulator. That's the chip that is generating the power in the transformer that generates the output voltage. This signals back through the opto-isolator to tell it to back off. You've now reached 5 volts on the output, or whatever value you set using these resistors. You've now reached that voltage and you've now got enough power, if you like. You're driving the transformer hard enough. When that opto-isolator signals back, the pulse width modulator will just back off a little bit, and by doing so it will maintain a voltage which you set using these two resistors. Let's have a look at the different package types you're likely to find. And a lot of power supplies, they are just the ones I've shown you in these little transistor-like packages, but these come in lots of shapes and sizes, so I'll just show you. There we have many different varieties. Some are like little ICs, some are surface mount, you can see them here. These are like the little SO23 surface mount transistor packages you can see. So sometimes these are TL431 and so on. Okay, so don't be surprised to find these in all different sort of shapes and sizes. And here is a fairly typical example of a switch mode power supply. This is your wall water type things, the little power packs that you get, and you see that the TL431 is connected in series with the LED and the opto isolator, and a resistor happens to be 1K on this one, much the same. This is ground. I know it sort of comes back up here, but this is ground. Okay, this is the transistor side of the opto isolator, and that is controlling the pulse width modulator. And it's the same setup. Those two resistors there and there, they have 10K, plus they've worked out some formula for the other one. These set the voltage at which this starts to conduct, and at that point the LED turns on. So that is the sort of thing you would find in real life, but as you can see, it is basically the same to the circuit we had. It has a few extra components for stability, but it is the same thing. Okay, so let's have a look how to test the TL431s, and also how to test this whole circuit on a power supply in circuit without removing components. How can we test the TL431? Well, the simplest way is with a little tester like this. So this is built on a little bit of Vero board. You can see it contains of a little pin header, 3 connections, a wire link, and a 1K resistor. And then we have 2 sets of wires. So if you look at it, the little wire link connects from one end of the pins to the other end, so from there to there, and the 1K resistor goes from the middle pin to this track. So this white wire here coming in, this is the supply voltage, and I can connect this to my bench power supply. The supply voltage doesn't really matter, 5 volts, 9 volts, whatever you fancy, because the TL431, if it's working, will regulate the voltage. So that we connect to the bench power supply with the white to the positive. The other wire, well, you can see the blue one is connected to the green, this is ground, and the other white wire goes to this end of the tester. But in actual fact, look, both ends are connected together by the wire link. So the middle one is ground, and both these are connected together. Same with the 1K resistor, and that goes to this white wire, and this is where we connect our multimeter. So to use the tester, we very simply connect a multimeter on here, we connect the power onto here, and we then just connect our TL431 across the pins, or the tracks if you like. Okay, either this side or this side. Now, it doesn't matter which way you put it round. If you remember from earlier, if you connect the reference to the cathode, the anode is in the middle. This is now a 2.5 volt regulator. So when I hold it against here or against here, the meter will read 2.5. If it reads 2.5, it's good. Let's try it. Here then is the tester, and here is a TL431. So we just connect the 3 pins to these pins or to the tracks, wherever is the easiest. My power supply is currently set to about 5.3 volts. I say it's not critical, but as long as it's more than 2.5. But I wouldn't set it too high either, otherwise the resistor will get very hot. We can connect this now across the pins, and when we get a connection, the meter will read 2.5. A little bit fiddly, just bend the leg a little bit. There. It's reading 2.6. That one's actually giving 2.6. The tolerance for these, well, it depends on if they are marked with A, B, or no letters after them. I think the A is actually 1%. So that actually seems slightly out of tolerance to me. As I mentioned, it doesn't matter which way round you put it. .48. It should read the same. Yeah, 2.48. I think my fingers, yeah, I had my fingers across the pins, which was affecting the reading. Okay, don't get your fingers on them. 2.48. 2.48. Okay, try another one. I have lots of these here. 2.49. All the way around, same. 2.49. So you can see with a very simple tester like this, we can test out with TL431. There we have it, 2.5. Again, all the way around, 2.5. So they're all good ones. Now the reason I made this with the 3 little pins here is because sometimes you can test them in circuit. This will tell you if they're good, usually. If they don't read good, it doesn't always mean they are bad. If they read good, they're good, okay? So here's a little power supply we had earlier. Here is our TL431, which is the 3 pins here. Okay, so we can try it. So as I say, if it reads good, it's definitely good. If it doesn't read good, you'll have to remove it and test it. It may be good, it may not. It depends on what components are around it in the circuit. Okay, that one reads 2.6. I'm confident that's actually a good one. Yeah, it's close enough. Once again, it doesn't really matter which way round you read it. We can go the opposite way around. 2.49, okay? So we can say that's a good one. So we can test them in circuit like that. If it still says 5 volts or something, the chances are it is faulty, but just take it out and just be sure. There may be something to do with components around it, like if it reads short again, take that and test it. Okay, that was just reading short because I had effectively just shorted the thing with the pins. So you can connect a little tester like that and test them in circuit. This is well worth building. You don't need a schematic, surely guys. This is like the original diagram I drew on paper with the reference pin and the cathode connected together, anode to ground, okay? Now you can also test this in circuit, the whole thing. So the TL431, the various resistors, the tracks, the continuity, the opto-isolator, the whole thing. And you can do this without powering up the power supply. So I'll show you how to do it. And this is very simple. You can do this on just about any switch mode power supply. And if you suspect the feedback thing isn't working, this is a very good test. To do this, first we need to connect our multimeter in diode mode across the opto-isolator. Now we want to connect it with the negative lead from the meter to ground. And we can also do this in resistance mode as well. Sometimes you have to try one or the other to get a good reading. So normally speaking, on a power supply, one end of the transistor in the opto-isolator, that's on the high voltage side, one of the pins will go to ground. In the case of this one, ground is a negative end of this large capacitor here. It's the negative of the bridge rectifier. And if we turn it upside down, we can see our opto-isolator here. And if you just follow this large track all the way round, there's the negative end of the large capacitor. That's the bridge. So this end of the opto-isolator is ground, and the easiest way to clip our meter leads on, because we need at least 3 hands to do this otherwise, is probably just attach it to this diode. So if you look on the other side, there's a diode there. This end is connecting to the negative end. This goes to the positive end of here. This is actually a Zener diode, and it's just to prevent high voltages appearing across the opto-isolator transistor. But it'll give us a good place to attach our meter. We could solder wires on, we could sprout a few extra hands and do it that way. But you'll see that we have a connection from here to here, and we have a connection from here to here. These are not shorted obviously, so I can clip my multimeter across this Zener diode. Okay, so I've attached the wires, you can see them there just across that diode, which is wired across the opto-isolator. I'm on diode mode at the moment, but I say we can also try resistance mode. Let's see what happens when we switch on the opto-isolator. And how are we going to do that? Well, we're going to do that by applying from our bench supply a voltage to the output of the power supply. And when the bench power supply voltage gets to around or just above, usually just above the supply voltage, that opto-isolator will turn on, because the feedback circuit will say there's enough output voltage. It's now trying to signal back to this pulse width modulator on the high voltage side, this chip. Okay, so I can connect my bench power supply, black to negative, red to positive. Okay, I'll just set this up where you can see the bench supply, and we're ready to go. I'll turn the power supply down. I'll actually turn the current limiter down a bit, but it's not important because nothing's going to draw any current really. Now you may wonder, is this going to damage the power supply? Well, the answer is no, as long as you don't go above the rated voltage of the output capacitors, or if you had the load attached, you don't go above the rated voltage of the power supply. Now, to test the feedback circuit, we want to go a bit above the rated output voltage. So disconnect whatever load is normally connected from the power supply. Yeah, disconnect it. If this is embedded in some device, maybe you can unplug a plug or just cut a track or something, but you need to be disconnected from the load. Okay, right, we switch on. You can see the bench power supply, no volts, no current. This is reading open. Right, let's start increasing the supply voltage. This is a 12 volt power supply. Yep, it's a 12 volt power supply. So when my bench supply gets up to 12 volts, we would expect the opto-isolator to switch, and this should read it. Let's have a look. Well, we're at 12 volts now. Let's go a bit higher. And there, got it. Okay. So just at the point we go above 12, I'll alter the fine voltage adjustment. 12.1, 12.2, there. Okay, come back down again, it's off. So you can see very clearly, I can test the whole feedback circuit of this power supply. There, okay. So if you ever suspect there's a problem with the feedback circuit on the switch mode that you're repairing, that is an extremely simple way to test that. Bear in mind, on some power supplies, such as ATX for example, the opto-isolator is only measuring one of the output rails or monitoring. On ATX, it's normally the 3.3 volt supply that is being monitored. But you do need to know, you need to be monitoring the correct supply. It's not difficult to work out if you're not sure if there's many outputs of a power supply. Just trace through the TL431, you'll be able to see it and figure out which voltage rail it's connecting to. Yeah. If you're really not sure, connect your power supply to each voltage rail in turn. Put a bit of voltage in, less than the lowest output voltage. Say you had a 3, 6 and 9 volt rail. Just go to the 3 volts, set it to 3. And just measure on the cathode of the TL431. If you see some voltage there, you know that is the rail which is being monitored. If you don't, just stick 3 volts into the 6 or the 9. You'll soon figure out which is the one you want to test. Okay guys, so that's how I test them. Now you should really know all about the TL431. It's not a mysterious thing. It's just effectively a Zener, which you can vary the voltage output by using 2 resistors, or just connect the reference to the cathode for 2.5 volts. You've seen how this circuit works. You can clearly see that with the Zener or TL431, the LED turns on at exactly the point you want it to do and sends a signal back into the other half of the circuit to regulate the output voltage. Hope you enjoyed that, and I hope you really think that is all you need to know about TL431 to fix stuff. And I look forward to seeing you all soon on another Learn Electronics Repair video. Ciao for now, guys.